All right, everybody. Welcome to the study group today. I'm happy to have you here. Uh, I hope this is informative. We're going to go over the X-ray beam today. We're going to talk about the ins and outs of what actually comes out of your X-ray machine and how it affects the body when it's attenuated with the X-ray. So let me switch over to a new screen and we'll get started here. Again, I appreciate you being here, and please let me know if you have any questions, and we'll go from there. So I hope you guys can hear me okay. If there's anybody out there listening, if you could let me know that you can hear me, that'd be great. All right. Well, I hope you guys can see that okay. Okay. All right. Here we go. So welcome to the LSRT study group number 6, the X-ray beam. So let's get started here. Like I say, if you have any questions, just raise your hand or speak up, or whatever is good for you. I'll be right back. Just want to make sure that's on. Okay. Okay, here we go. Okay, so I wanted to just real quickly do a quick review of last week. In case you weren't able to see it, we talked about the actual production of the X-ray photons. I just want to run through that real quick. If you have any questions, let me know, then we'll get started on this class. It shouldn't take real long, so just hang with me, okay? So we talked about the X-ray tube and what happens inside the X-ray tube. This poor drawing here is the actual X-ray tube. You can see it right there. So what happens is we get electricity from just a 110 outlet. It goes into a generator over here, and it's actually stepped up to a higher energy level. And it comes through the cathode right here and files down to something called the filament right there. It's a little tungsten coil wire, and it heats up to a couple thousand degrees. It's really, really hot, to the point where it boils off negatively charged electrons, which is this electron cloud right here. That process is called thermionic emission. And as what happens is those electrons come across the tube, negatively charged electrons come across the tube due to current tube potential. So it comes over here to the anode. Now the anode is made of a tungsten alloy. Sometimes it's rhodium, sometimes it's molybdenum, but most of the time it's tungsten. So the electrons are actually attracted from the cathode to the anode because the anode is positively charged where the cathode is negatively charged. We know that negatives attract. And these come across the tube extremely fast, and it hits a part of the anode right here called the focal spot. Okay, now when it hits the focal spot, that's where the interaction between the electrons and the atoms take place. Okay, now the anode right here is rotating about 3,000 RPMs, which is what you can hear when you hit the prep button on your X-ray machine. You can hear that rotor just a spinning. So that's the anode plate spinning, and the reason it spins is to reduce the wear on the anode. If it was just hitting one spot all the time, it would end up cracking the anode and we'd be in trouble. So it spins to help disperse that heat. So the interaction takes place and heat is converted to X-ray photons. Okay. Only 99% or 1% of the electrons that come across there are converted to X-ray photons. Okay. And those X-ray photons are funneled down into filtration device. Filtration takes away the weaker X-ray photons, and only the strong ones come through here, through the collimator right here, down to the patient, through the patient, and into the image receptor right here. Okay. Now the components of the X-ray tube, you kind of just be aware of those. Around the tube, it's actually a glass Pyrex Corningware type glass, really hard. The glass enclosure right here, where the cathode and anode reside, is completely void of any type of air or gas. It's a vacuum, basically. You wouldn't survive in there if you shrunk down and went in there. Okay, now the rotor is turned by something called the stator. It's electromagnetically turns that rotor through various ball bearings, which are steel plated, that help disperse heat as well. Now the stem that comes across there, that turns the anode to help us to help us make X-rays. Okay. Now the outside of the glass or the lead-lined tube is filled with oil, and the reason that is to help disperse heat. Okay. And we also know that the metal tube is lead-lined to help protect scatter radiation from going all over, because as we're going to talk about today, the X-ray tube actually produces X-rays in every different direction. Okay, that's why we have a metal-lined or lead-lined metal housing across there. Okay, so that's just in a nutshell kind of how that works. If you have any questions, please reach out. It's really interesting the way that X-rays are made. It's pretty neat, and when it's boiled down to its simple form, it's not too bad. So, okay, let's get started here. Okay, we're just going to run through some vocabulary like we normally do about the X-ray beam. So we know that the X-ray beam is a stream of high electromagnetic radiation which can pass through solid objects. Okay, and this beam is made of X-ray photons. Okay, a photon is a small bundle of energy in its simplest form. That's what it is. Frequency, the number of X-ray waves that pass a fixed point per second. Okay, and we'll talk a little bit more about that. X-ray uses very high wavelengths, short wavelengths actually. Wavelength, the distance between successive crests of a wave, so up and down like this. Okay, and the higher the wavelength, the lower the frequency, and vice versa. The lower the wavelength, the higher the frequency. The higher the wavelength, the lower the frequency. Okay, beam quality. Okay, you'll need to know what quality and quantity are, and we're going to talk about that. So the quality refers to the power of the X-ray beam. This is primarily determined by the kVp. Higher the kVp, the higher quality and higher penetration of your X-ray beam. Beam quantity is the number of X-ray photons present in the beam, and this is determined by the mass, the milliampereseconds. Okay, and the higher the mass, the more X-ray photons are present. Okay, pretty simple. So just remember that the quality is kVp, quantity is mass. Quantity is the amount of X-ray photons, which is determined by your mass. And beam quality refers to the kVp, which is the energy of the X-ray beam. Higher kVp, higher the energy. Okay, kVp is a kilovolt potential. Mass is milliampereseconds, and we come to the milliampereseconds by timesing milliamperes with the exposure time, and we'll talk a little bit more about that. Okay, isotropic. X-rays are produced equally in all directions. That's interesting. because we look at the X-ray tube and it shows the X-ray beam coming down out of the collimator. But those X-rays are produced equally in all different directions. Okay, thus the need for a lead lime tube, so to protect from leakage radiation. Polyenergetic, millions of X-ray photons with a wide array of energies. So we'll talk more about that as well. Okay, primary beam. It's pretty simple. It's an X-ray beam that leaves the X-ray tube. That's your primary beam. Okay. The remnant beam or exit radiation, the portion of the X-ray beam that remains after it passes through the patient's body. So after it passes through the patient's body, it hits the image receptor and we get a late image on that image receptor. That is due to the remnant or exit radiation. Okay, we'll need to know about the inverse square law. The intensity of the X-ray beam is proportional to the square of the distance of the source. Okay, so we'll talk about that in a minute. But yeah, inverse square law. And the fundamental properties of the X-ray beam: a form of electromagnetic radiation with a very short wavelength, which means if it's short, we're going to have a high frequency, traveling in a straight line at the speed of light, having high energy, the ability to pass through most materials, including some opaque materials, causing ionization. So ionization is a reaction with an atom inside your body. Okay, and it's invisible to the naked eye, so you can't see the X-rays. Sometimes that'd be cool if we could see what was actually going on. They also carry no electrical charge, so it's not going to shock anybody, and is produced with high voltage in the X-ray tube. Okay, we kind of learned about that last week. High voltage. Okay, let's talk about photon interactions with matter. And when I say matter, I mean the human body. We're in the business of imaging the body, right? So we're going to talk about what happens when that photon actually hits the body. Okay, photoelectric interaction. That's the main reaction that happens. It occurs when an X-ray photon interacts directly with an inner shell of an atom. Okay, this occurs with attenuation of tissue. So attenuation is the actual X-ray photons going through the body. Okay, that's attenuation. Compton interaction. This is where things can get scary sometimes. Compton interaction is a type of scattering that occurs when an X-ray photon partial energy collides with an electron in an atom. So Compton scatter is the #1 source of occupational dose. The more matter, the more scatter. That's kind of a saying in X-ray. If the patient's bigger, you're going to get more scatter. And we're going to talk about a couple things that we can do to help remediate that. Coherent interaction. It's also known as Rayleigh interaction. It's an interaction between an X-ray photon and the entire atom, and the energy is released as a scatter photon. Most coherent actions are absorbed in the body and do not contribute to the image. Okay, so we know that right away that coherent is kind of a weaker reaction or a weaker energy source. Okay, coherent scatter occurs at lower energy levels. Okay, we talked about attenuation, the decrease in X-ray intensity as it passes through the body or matter. Okay, types of tissue, part thickness, and tissue type determine the attenuation accomplished by the X-ray beam, which we've kind of learned along the way. We have to make adjustments to our technique with the size of the patient. Okay, and it has everything to do with attenuation, how that reacts in our body, and what kind of image we get afterwards. Okay, so let's talk about frequency and wavelength. So we already learned that the X-ray beam has a lot to do with wavelengths, right? So the shorter the wavelength, the higher the frequency will be. Okay, making the beam more intense, increasing the ability to pass through dense body parts. So we want to work with a shorter wavelength and a higher frequency, right? So we can get through the body part that we need to. So, and conversely, the longer the wavelength, the lower the frequency will be, making the beam less intense and less apt to pass through the given body part. Okay, and down here, there's kind of a spectrum that goes through different types of radiations, right? And you'll know that radioactive sources and medical x-rays, you can see the wavelength down here, and you can see that the wavelengths get shorter and shorter and shorter, which is going to bring the frequency down. Okay, sunlight's just a little bit shorter or a little bit longer than medical x-rays, and we've got visible light, microwave, FM, AM radio. We get out here on AM radio, and the wavelength is actually extremely long, so it's pretty weak. But the tighter that wavelength gets, we're going to get more energy, okay, and be able to produce medical x-rays, okay. But the thing you need to remember is the shorter the wavelength, the higher the frequency, okay. The longer the wavelength, the shorter the frequency, or the lower the frequency, okay. All right. Okay, X-ray beam characteristics, quality and quantity of the X-ray beam. So we've learned that quality is governed by KVP. Okay, the higher the KVP setting, the higher the quality of the X-ray beam, giving the beam more penetrating energy or more to easily pass through what it needs to pass through, or dense tissues. That's quality. Increasing KVP increases the average energy of the X-ray beam. That's something you need to kind of drill into your head. Increasing KVP increases the average energy of the X-ray beam. Okay, KVP determines the energy of electrons bombarding the anode. Okay, so say we're doing a chest X-ray and we're using a really high KVP. We are bombarding that anode with highly energized electrons. Okay, so the more KVP we give, the higher energy of our electrons hitting that anode. Okay, so quantity is governed by mass. Okay, milliamperes seconds. The higher the mass, the higher the quantity of X-ray photons. So this is the number of X-ray photons that we are throwing at the anode. The more we throw up there, the more X-ray photons we're going to have. Okay, mass is calculated by multiplying the current, which is the MA. You can look on your individual machine. There's going to be a setting for MA, and there's going to be a setting for seconds. And then you multiply those, and that's going to be your mass. Okay, and the math is what we go off on our machines. Fortunately, we don't have to do a lot of math. It's all done for you, which is nice. So MA controls the number of electrons passing through the X-ray tube. Okay, and the exposure time is the duration of that X-ray exposure. Okay, I know when we used to do ribs, we used to do exposure times that were longer than the second. 1.5, 2 seconds, which in X-ray terms, that's a really long exposure. So what we're doing there is we're bombarding the anode with electrons. Okay, the quantity of electrons, we're getting a little more out of it. So the thing you need to remember though is quality is governed by KVP, and it's the energy of the X-ray tube. Okay. And the quantity is governed by the mass, and that is the number of photons that we end up with. Okay, those are beam characteristics. So here's a little depiction of the X-ray beam. So as we discussed last week, the beam comes out of the X-ray tube, and we won't go through that again, but you can see that it goes up at an angle. Okay, and this is the primary radiation beam before it hits the patient. Okay, and then we get back here, and this is the remnant or exit radiation back here. Okay, and here's the detector or the IR. Okay, pretty simple stuff. Okay. So a remnant beam, we just talked about that. Here's another depiction of that. We've got the X-ray beam coming down to our patient, right? It's attenuated in the patient, and some of those react and they are exited a scatter radiation, which we'll talk a little bit more. We see scatter radiation coming from the patient right here. Okay. And then the photons that are hitting the IR are actually exit radiation or remnant radiation. And that's where we get our latent image, the image we see on the computer. Okay. Okay. All right, the inverse square law. Okay, here's a little depiction that kind of shows you that a little bit better. As you move further away from the source of radiation, the energy drops rapidly based on the square of the distance increased. Doubling the distance will give you 1/4 of the energy that you started with. Okay, that's a good rule of thumb. Example would be flashlight. You know how you have a flashlight, you put it against your hand and it's really strong. Okay. Now, when we back that flashlight out, our light is going to get bigger or magnify, but the light is actually going to get a little bit dimmer, right? Because we're losing energy. And that's the inverse square law. And the only time you really use this is if you're shooting at a longer distance, 72 inches, you need to make adjustments to your KVP, which we do with the chest X-ray. We put it right up there. That gives us more energy to come across that distance, right? I hope that kind of makes sense to you. So the higher the KVP, the more energy we're going to have to cross that distance. Where we're shooting at 40 inches, you know, the average is between 55 and 75 KVP because we just don't need as much energy to get across that shorter distance. Okay. But that's the inverse square law in a nutshell. The further you get away, the energy drops rapidly, and it's based on the square distance from the energy source, which is the X-ray tube. So doubling your distance, you will have 1/4 of the energy you started with. Okay. All right. I'm not getting too deep into some of this stuff. I don't want to overwhelm you, just so you have an idea of what these things are. Okay. The properties of the X-ray beam. Now, if you've kind of noticed through this, you can see that the X-ray beam is extremely efficient. You know, it does the job it needs to do. And let's talk about what those properties are. Okay, electromagnetic photons of radiation. Okay, emitted with various energies and wavelengths, and it's not detectable to human senses, so you can't feel or you can't touch it. They travel radially from the source, you know, in straight lines and at the speed of light, so it happens really fast. Okay. These electrons can travel in a vacuum. That's what they do in the X-ray machine. Display differential attenuation by matter. And we'll talk a little bit more about that in a minute. The shorter the wavelength, the higher the energy, and hence more penetration. Okay, so the shorter our wavelengths get, there's less frequency, right? And the higher the energy. Okay. Ionization, you know, that's the interaction that happens when the X-ray photons actually hit the atoms in the body. And we'll talk about that a little bit. That's called ionization. And it produces a latent image on the film detector. So extremely efficient. Pretty cool. Okay, photon interactions with matter. Photoelectric interaction. X-ray photons collide with an inner shell of the electron, transferring all of its energy and ejecting it from the atom. And this is usually characteristic radiation, which we talked a little bit last week. So the photoelectronic, we've got an incident X-ray photon coming along, enters the body, and it hits the inner electron here. And it actually hits it with all force. There's no energy lost, and it spits out that as an electric photo or a photoelectron. Okay, and these are the ones that we get our image from. So photoelectric, remember that, and it's when a photon collides with the inner shell of an atom. Okay, and pops that electron out with the same energy in which it came in with. Okay, all right. So the next interaction is Compton interaction or Compton scatter, and you're going to hear Compton quite a bit. It's important that you know what that is. The photon partially collides with an outer valence electron right here. Okay, so it hits that, but it doesn't hit it with all the energy, right? Because what happens is the electron comes out here, and it's called a Compton electron, okay, or a Compton recoil electron, and that can give us part of our latent image, okay? But at the same time, seems though it wasn't hit with the energy, it was a partial hit on the electron, it actually spits out a scatter photon. Now, scatter photons, they can go every direction. So we've got a photon coming into the body, it interacts with a cell, okay, or the outer valence electron of an atom, and it spits out a Compton electron, which is good radiation, but it also spits out a scatter photon. So scatter can come out of all sides of the body, okay? And this is the number one source of occupational dose. If you're in the room helping hold somebody for a good position, you have to worry about scatter radiation. It's not so much the actual X-ray beam itself, is what happens after it hits the body, okay? Scatter radiation is produced, and it can actually degrade the diagnostic images, especially when they go down into the image receptor. They'll give us unsharpness, non-contrasty pictures. So we'll talk a little bit more about that in a second. But the thing you need to know is scatter radiation, Compton scatter, comes from a indirect hit on a valence electron, okay? And it scatters in every single direction. There's millions of reactions going on, okay? And I might add that the Compton electron is what contributes to the patient dose or can damage the cell of the body, okay? And with each X-ray, there's millions of interactions happening, okay? It's not just one, but this is what happens in one, okay? So that's Compton scatter. I hope it's hard for me to explain that sometimes. So let's talk about reducing the effects of Compton scatter. And we already said, you know, the bigger the patient, the more scatter you can have. And a lot of times there's nothing you can do to combat that aside from protect the patient and protect yourself when needed, okay? So there's a couple things that we can do, and you know, this first one isn't as common as it used to be. So when I went through school, we had compression bands. That if we had a bigger patient on the table or standing up, we'd actually put a compression band around them, and what it would do is it would compress the body down. Okay, it's going to make less tissue for us to go through, thus giving us less scatter radiation. Okay, another way we can combat that is use a smaller field size, or like I harp on all the time is we need to be collimating as tight as we can. So the tighter we collimate, the less tissue we're gonna radiate and the less scatter radiations we're gonna get. Okay, and I always say, you know, if we're shooting our images with a wide open collimation, we're gonna have tons of scatter. And I kind of talked about how that works as the scatter comes out of the body, and it can enter the image receptor and really wreak havoc on our image. Like I said, less recorded detail, less contrast, and just a lot of noise on your image. You'll note that when we shoot an abdomen on a larger patient, our image just doesn't look sharp. Okay, there's no detail between different tissue types, and that's because of the scatter radiation. Another way we can combat that, well, the main way is to collimate and use a smaller field size. Okay, another one is to use a lower kVp. So we understand that the higher the kVp, the higher the energy of the X-ray beam, which is going to cause more scatter radiation. Okay, so use a lower kVp when possible. It's going to be a little more dose for the patient because we're using a higher mass, but you're going to get a better image out of it. You know, with fingers and wrists and stuff like that, we really don't have to worry too much about it. Other than if you collimate well, you're going to get a really nice picture. So, so let's see. So at times, like I said, it's just not possible. You got a big patient in there. Sometimes you're just going to have to live with what you get. But if you try these things, it's going to help. We're going to get a better picture out of it. Okay. So higher kVp equals more scatter equals decreased contrast. It's as simple as that. Lower kVp equals less scatter and increased contrast. So, you know, it's an ongoing debate in radiology. There's a fine line between what level of kVp you use and still getting an optimal image. You know, I'm in the camp of using a little bit lower kVp and getting a better diagnostic image. Which as we go forward, we'll learn more about technique work. But those are some ways we can reduce Compton scatter. Okay. Now the third type of interaction is called coherent or Rayleigh. Okay. So what happens with Rayleigh or coherent interaction? The photon actually interacts with the entire atom. Okay. It doesn't hit just one electron or valence electron, which would cause the Compton scatter, or an inner electron, a direct hit, which would cause photoelectric interaction. Coherent, it doesn't hit an electron. It actually interacts with the entire atom. So what it does, it gets in there and it kind of shakes that atom, okay? And there is scatter that's released, but it's a really, really low energy. I should note that most coherent scattering comes from a low energy X-ray. So let's read what it says here. X-ray photons interact with, it should say atom there. The energy of the electron is raised, so the energy of the actual atom is raised, but it doesn't eject an electron. Okay, it actually ejects scatter radiation at a lower level, and most of the time this interaction is absorbed by the body and it doesn't reach the image receptor, so it really doesn't do much. It's just absorbed by the body and doesn't reach the image receptor. Okay. All right, so yeah, you can kind of see that it's coming in and hitting the atom. Now that atom is going to get excited, but it's not going to release an electron because we didn't hit an electron. Okay, it's actually going to just release the same amount of energy that come in as scatter radiation, but it's usually absorbed by the body. Okay, hope that makes sense. Okay, that's coherent interaction. Just remember that one. So we've got three different types. We've got photoelectric, we've got Compton, and we've got coherent or Rayleigh. And the thing you need to remember is Compton is the more dangerous, does more damage to the body, and does more damage to your actual X-ray film or image. Okay. Okay, attenuation. All right, we kind of talked about this a little bit. The amount of attenuation depends on the material's atomic number, uh, density, and energy of the X-ray beam. So we see right here, we're going to say this object right here is the human abdomen, maybe. So we've got all these X-ray photons, millions and millions of them coming to the body. Once it hits the body, it's attenuated, okay? So there's bone, there's muscle, there's fat, there's air. All these are going to attenuate a little bit differently just due to their atomic number, okay? The denser the material, the less apt the X-ray is going to get through that, okay? Fat, air, some muscle, it's going to pass through there fairly easily, okay? So the less dense the body part, the easier the X-rays are going to pass through there and reach the image receptor. So what happens when it hits a bone is it's primarily stopped, the X-ray photons, but it still casts a shadow on your image, okay? Boiled down to its simplest form, it's pretty simple. The denser the material, the less apt the X-ray photons are to make it through that to the image receptor, okay? All right. And we do not need to know the atomic numbers of different tissue types or anything like that. Just suffice it to say that bone is denser than fat, okay? And it's going to easily pass through fat, whereas bone or a dense material like the heart or the liver, it's not going to pass through that as easily. And it's going to show that on the image, okay? All right, so attenuation of tissues. The contrast between tissues in the image is generated by the difference between the atomic number and tissue thickness, is what we just talked about. So the factors that affect attenuation is tissue composition, what type of cells are within the tissue, influence how easily the tissue can be attenuated or how easy the X-ray photons can pass through that. The frequency of the X-ray beam, higher the frequency, it's going to attenuate more readily in tissue, okay? So tissue thickness, the greater the tissue thickness, the more attenuation that occurs, okay? Pretty simple once you stop and think about that. The thicker the tissue, the more your body's going to attenuate that or absorb it, and it's going to show that on the latent image, okay? Types of tissue. So here we've got tissue types in order of from least thick to more dense, okay? So we've got air, and that's going to show up black on our image, okay? Fat's going to show up a little bit lighter than that. Soft tissue a little bit lighter yet. Calcium or bone is going to show up even lighter. X-ray contrast, which we don't deal with here. Contrast is something we inject into the body to help us see structures a little bit better. We just don't use that here. Anyway, it's got a really opaque, high atomic number, so it's going to show up lighter on a film. Metal is going to be really, really white, okay? It helps us when we're looking for metallic foreign bodies. Okay, hope that made it seem a little bit more easy. So let's look at a chest X-ray, and we can kind of talk about the attenuation that's happened in this X-ray. Okay, this is a really contrasty chest X-ray. I'd like it a little bit lighter than that, but it is what it is. So let's start with air. Okay, we've got the lungs that are filled with air. We've also got a gastric bubble here, and those are air. So the X-ray photons actually pass through pretty readily and are able to reach the image receptor, thus giving a black latent image, okay? We've got muscle. We've got a very large muscle right here called the heart. Okay, you can tell that it's more dense, right? So the body attenuated the X-ray photons in the heart, right? So less X-ray photons hit the image receptor, thus making it lighter. Okay, we've got bone. It's really a light gray. just because they're dense. And you'll know when you shoot an X-ray on a 90-year-old woman or man, those bones are going to seem more gray, and that's just due to loss of calcium. The atomic number has actually gone down in their bones, so it's readily passed through by X-ray, not attenuated as much. Okay, we've got the liver right here, very dense organ. That's why it shows up so light. We've got the trachea coming down right here. You can see where it bifurcates into both lungs, and you can see that that's a darker color. So we know that the trachea is full of air, filling those lungs up. There's markings in the lungs, they're a little bit lighter. It's just a little more dense material. Okay, and like I say, the gastric bubble inside the stomach, ribs are a little bit denser, higher atomic number. That's why they're showing up a little bit lighter. Okay, I hope that makes sense about attenuation and how that works with X-ray. I hope this was informative. I know this stuff's kind of hard to grasp sometimes, but as long as you can remember what the interactions are once the X-ray beam hits the body, okay? Just remember that the X-ray photons are coming across, millions and millions of them, and they're going to hit the body, and they're going to hit atoms within the body, and 3 different interactions are going to take place. The photoelectric is a direct hit on an inner shell electron of an atom, and it is released as such as an X-ray or as a photon that's going to make its way, if it's heading that direction, make its way down to the image receptor and give us an image. For bigger patients, but there is a little bit of Compton scatter with everybody, it's going to go in there, it's going to partially hit an outer valence electron, and a Compton electron is going to be released, which helps with our latent image as well. But some of that energy is lost due to scatter radiation, and it's going to shoot out a scatter photon, which is going to come out of the body whichever direction it needs to. Okay, so like I say, they come out in every direction. If they come out towards you and you're out there, you're going to absorb that dose of X-ray. Like I said, this is the #1 source of X-ray dose for us as occupational workers. So you really have to protect yourself when you're out there. And then there's coherent, where it just hits the atom, reacts with the atom, but doesn't release a photoelectric electron. Okay, it does release, however, a low energy scatter photon, which is usually just absorbed by the body. Okay, if you can get those little key things down, you're going to be okay when it comes to the physics of how the X-ray beam interacts with the body. Okay, inverse square law, the further you get away from the X-ray source, the weaker the energy is going to be. So like I said, when we're shooting a chest X-ray, we're out here at 120, 115 or kVp. We need that energy to make it across that distance and give us an image. We talked a little bit about tissues, how tissues are attenuated and how that translate to the image that we get. Bone being more dense, or fat and muscle are less dense and are easily passed through, where bone isn't so much. Okay. Frequency and wavelength. The thing you need to remember there is the shorter the wavelength, the higher the frequency. So the longer the wavelength, the shorter the frequency, right? Okay, and we work with short wavelengths in X-ray, okay? And you can see that here. So, okay, and I will be sending this out as a shared document. and you guys can go through this when you need to and just get familiar with the vocabulary. My books are just about done. They're all copied. Some of them are put together. But when you get that study guide, it's going to have all this in it, okay? In a little bit different format, but you can take notes in that book or whatever you need to. And hopefully within the next week, we'll get those out to you. I know I've been saying that for a hot minute, but life gets busy, okay? All right, so a little bit of SpongeBob, my counterpart's favorite cartoon character. What's the transfer of heat by electromagnetic waves? Radiation. Okay, that's X-ray in a nutshell. Okay, guys. Well, that is all I have for you tonight or today. I hope you guys have a good rest of your week, and I hope that this was somewhat informative for you. If you have any questions, please let me know. And thank you guys so much for coming. You guys have a good day. Okay, we will be another positioning video here shortly. It'll be of the shoulder. Hopefully that one will be helpful for you guys. Make sure you guys are watching that and liking it and answering the questions. Okay. Thanks for your time. Appreciate your time and your hard work. Okay. We'll see you guys.